Okay. So at the end of the last meeting, we had introduced this policy iteration algorithm. And this followed from, we had already established the policy improvement theorem, which was a method where, given a policy and its value function, we can define a new policy which is guaranteed to be better than the previous policy, meaning it has a higher value function at all of the states in the problem. So policy iteration is just a way to make use of the policy improvement theorem to eventually arrive at the optimal policy and value function. And the algorithm here written out just conceptually, it's just a series of steps where we alternate between evaluating a policy that we've already defined. Here we start with some initial policy, which could be random. We can always easily define the uniformly random policy. And then we evaluate it to get the value function of that policy. And to do that, this is the first algorithm we looked at, which was the iterative policy evaluation algorithm, right? So we use this to actually calculate the value function of the starting policy. And then we do the improvement step where we use the policy improvement theorem and we pick a new policy which is greedy with respect to the old policy, right? And that's what was being shown here in this table, which is this was the value function that had converged for the random policy on this grid world example. And then this was the greedy policy with respect to the value function, where we just choose a policy which takes us to the highest value state possible. And we can always do that if we know how the environment works and we have this value function. We can just look at all the possible actions that we take from every state, and we choose the action which results in the highest value for that one step ahead. So the magic of this is that we only have to look sort of one step into the future to get all the information we need to improve the policy, rather than actually looking, infinitely many steps in the future at all the possibilities. We only have to look at this branching, one step into the future. And that's what this argmax function did here, right? We're looking at the argmax over all the actions of all these one-step transitions. Okay, so that is the whole point of why we calculate the value function. So that's what's being shown. So once we do that, the point is eventually this process will converge where we won't see any change in either the value function or the policy, meaning the policy is already greedy with respect to the value function. And when we reach that point, it means that we have the optimal policy, because it means that policy, that value function meets the criteria of the Bellman optimality equation. And there's a unique value function that meets that criteria, and that has to be the optimal policy. So here, this is just define some pseudocode for the policy iteration algorithm, and we alternate between policy evaluation and improvement, where here's where we choose the argmax and we define the new policy, and we do this until the policy is stable. And then we have both the value function and the policy. Now, there was an exercise that related to this, saying this isn't the only stop criteria we have. This is saying, like, once the policy is stable, there's actually a whole family of policies that are optimal. Like this argmax function, there's not necessarily one unique argmax. There could be many actions that all share the same argmax, in which case there's a whole family of policies that are optimal. We can choose any number of those optimal actions. So another way to terminate this is to look at the value function, because we're going to get a new value function every iteration. And if the value function stops changing, the process is also converged. So we can either look for the policy being stable or the value function being stable. Either way, one or the other would be sufficient to know that this algorithm has converged. So if you're confused by any of this, I mean, this whole algorithm relies on everything we did in the last session. So yeah, you should look at the material from that or the video from that. But for anyone that's already done that and still has a question about how policy iteration works, you can ask it now. If not, we're going to move on to the first example we're going to solve, this car rental example. But on the left side here, these are notes of just my like implementation of all the stuff to do policy iteration. Yeah, I'm not going to go over it in detail here because actually I have this version of the code. I have a different version of the code in this summary notebook where I redid some things, but the code I have here does very closely match the algorithms like in the book, in the sense of like the policy or the dynamics equation, like the probability transition function for the environment here. I have it's this like 4-argument function, and this isn't like the most efficient way of doing it, but if you look at the code in here, it does sort of match exactly what's being done in all the pseudocode in the book. There's some simplifications you can make of this, which I have done in this notebook. You don't actually need this full 4-argument function. You can get away with simplifying it a little bit. But here, the policy iteration, well, this is just written as a recursive function, but you can see that it alternates between the policy evaluation and then, doing the policy improvement step. So like conceptually, it's just this alternating between these two steps until, it converges, like your policy stable, and then it's done. So before we do the Jack's car rental example, we can look back at the grid world example we had before. So remember, this grid world is just a grid world where you have a reward of -1 for every step, and then you terminate when you reach the corner. So the optimal policy is just one that reaches the corner as quickly as possible. So we can see here that if we do policy iteration, we start with the random policy, right? Being shown here. So what's being shown here is the policy we have, and then on the left side is the value function that we've converged for that policy. The random policy, this is the value function. Then on the next step, this is the greedy policy with respect to this value function. And we can see that actually we already have the optimal policy here. We can go one step further and see that there's a slight change to the policy here. Notice that now, like for this policy, the 2 squares here, these 2 actions are considered optimal. And here, actually, all 4 of these are optimal. So, but this is still the optimal policy, right? All 4 of these actions are optimal. So we don't have to choose between all of them. We could easily just pick one of them. The reason why all 4 here is because if you look at this square, like if you look at this value function here, notice how if we go up, down, left, or right, we get to a value of -2. And these are all equally good values. Whereas if we look here, this policy was greedy with respect to this value function. And for the random policy, it actually looks like it's better to go to this square or this square, right? Because they have a value of -18 each, and these are -20. So it's only when you do another round of policy iteration that you see that actually these are also equally good. But it's just lucky that this policy is already optimal, and you can see that it's already optimal because the value function here doesn't change, right? From step 2 to 3, they're all the same values. And the values here also match, this is just the L1 distance to the corner, right? So it's like how many steps we need to make to get to either this corner or this corner, right? So here it's just 1 step, here it's 2, and the worst is 3 because we go 1 over and 2 down. So it's just like this New York City block distance to each corner. So does that make sense to people for the really simple example of this grid world? How policy iteration works? Okay, so I guess we'll move on to the car rental example. This example, I guess this paragraph describes the whole problem. It's a little, you have to read it a few times to really get it. I have it sort of in bullet points here to make it a little simpler. But the idea is we have two locations to rent cars from, and customers will arrive at each location. And there's a probabilistic model for how many customers we expect to arrive at each location. It's a Poisson process here. And these parameters like lambda controls the Poisson distribution. So depending on the location, we have location A and B, and there is basically four different probability models. There's a return and a request model for both location A and B. So it tells us the probability of a customer either returning a car or requesting a car at each location. So this is like given to us, we're told. And then during the course of a day, we will have a certain number of cars rented and returned at a location. And then at the end of the day, each location will have, a set number of cars. And the action we have to take is to prepare for the following day. And the way we prepare for the following day is we decide to, move cars between locations. So the point is we want to make sure that there's enough cars at each location so that we don't, needlessly turn away customers. But we can't just do it freely because there is a cost to transferring cars. And here, so this problem is stepped where like each step is a full day. And then the state space is the number of cars at each location at the end of the day at, locations A and B. The action space is how many cars we can move. We're also limited in how many we can move. So we can move a maximum of 5 cars in either direction. So the way the action space here is defined is -5 to 5, where -5 means transferring 5 cars from B to A, and 5 would mean transferring 5 cars from A to B. So there's a maximum of 11 actions. And of course, we can't transfer more cars than we have. So it is limited by, the number of cars that are actually at each location at the end of the day. Also, we can only have 20 cars at each location at the end of the day. So if there's more than 20 cars left at the end of the day, then those cars are just, sent back to some other unspecified place. And then, this is during the day how the cars are requested and returned. If we get a car returned during the day, we can't just immediately rent it out. So there's some turnover time. So that car would either be available to rent at that location the next day, or we could transfer it to the other location. And then we're going to use a discount rate of 0.9, but this is a continuing problem. So we basically get a $10 reward for each car that we rent. And the reason why we have to use this discount rate is because we're assuming this is just this rental company is going to operate forever. So we're just looking to maximize the long-term return, but we're discounting future monetary reward by this factor of point. So it's 0.9 per day. So basically money is worth 10% less every future day that we go. And then there's a $2 cost every time we move a car, right? So we can't just freely choose actions without any cost. So actually, turning all this into the actual problem is the hard part of doing this wrong. Because you have to take all this information and turn it into, really, we have to turn it into this, which is, the probability transition function. So we have to understand for a given number of cars at each location, and then if we decide to move the cars, what do we expect the state to end up in at the end of the following day? And that involves understanding, the probability of every type of customer arriving, either request a car, and then if there's too many requesting, we don't get to rent those out. So this function here is what generates this P matrix, right? So really what this does is compute the probability of, all of these 4 arguments. And it's kind of, cumbersome. It does involve using this Poisson equation. Luckily, since we have the Poisson distribution here. We know the exact probability of every n value for the customers. And yeah, if you look at this, this is just making over time, it's just iterating through all the possibilities and making a big dictionary lookup of all the probabilities. So, we end up with this. Let's see, this is an example of, yeah, I mean, if you want to see like the actual details, you can see this is a very sparse matrix, but this whole thing, this, PTF here, right? This 4-dimensional array is what contains all of these probabilities. And you could see the reason why this isn't the most efficient way of doing this is because you can see how sparse this matrix is. You're actually better off just only, saving the values that have non-zero probability and having a way of keeping track of that. But, because we don't really care about the ones that are zero probability. We just need a way of iterating through the options that are actually available to us. So anyway, but here's the finite MDP. There's 441 states in the problem, and then these are the 11 actions. And then, oh yeah, another reason why this is such a large matrix is because I also have, even the reward space here is this discrete space of like 189 possible reward values. This is the part you don't actually need to do this. You can get away with just having average rewards for the transitions. So that reduces the amount of stuff you have to store by quite a lot. But anyway, so you do that, you can define the problem. And then once you define the problem, you can just apply this generic policy iteration algorithm, right? We don't have to change this algorithm to accommodate our problem. We just use it the same exact way. I mean, here, I have it, working on the grid world example, right? Where we have these 3 steps. And here, once I define this, I just plug it into the same algorithm. And this is the exact same type of solution as we had for the grid world, except for now we have a more complicated looking policy function, right? So here, these policy functions are being shown as heat maps where, the value here, this is the integer, which tells you how to move the cars. And then the state space here is this 2-dimensional grid, which is the number of cars that are at location A and B. So, right, it's the same information which is shown here. So we can have 0 to 20 cars at each location. And then all of these gray squares in the middle, these are all of the states where you don't actually move cars, or you shouldn't move cars. And that's because the cost of moving the cars is actually, not worth it for the benefit you get. And really, I mean, it's not too surprising that it only becomes worth moving the cars when you get these really extreme lopsided states, where here it's like, we have 20 cars at location A and 0 cars at location A and 20 at location B. And then, that's when it's advantageous to move them. So what this is showing is the policy we get on each step of policy iteration. And then the final graph here is the value function for what is the optimal policy, which is the last one here. And we can see for the optimal policy, like the value here is like the worst state we could be in, not too surprisingly, is having 0 cars at both locations, right? Because if we have 0 cars at both locations, we have no cars to rent, and we just have to wait until cars are returned to us. And then, the best possible situation is having 20 cars at each location, because then, we're guaranteed basically to be able to rent the maximum amount of cars to any customers that show up. So yeah, this is any questions about this solution, what it looks like, or how, policy iteration for this?
Can you go over the heat map? What does it mean to not have to move cars? How does that relate to the policy?
The policy function is the number of cars that you move. Like those are, so the policy tells you the action to take. In this case, the action to take is how to move cars. So, right, I've defined it from -5 to 5. So if the optimal action is 0, that just means that the optimal action is not to move cars in that situation.
Oh, and the positive, negative in the two locations would be.
Yeah, well, I mean, that's what I wrote here, right? So just for simplicity, right, negative numbers mean transferring from B to A, positives transferring from A to B. So that way you don't have to, have like the action space is like two different values.
Okay.
Right. Because moving, like you would never move 3 cars from A to B and 3 from B to A. Like, right. That's a worthless transfer to make because that's the same as keeping the number the same at each location.
Oh, okay. I get it.
Say, Jason,
Uh-huh.
can you hear me?
Yep.
Oh, great. In this case, the policy was just a numeric value, but
Yep.
is it possible that
Negative
the policy,
11.
right?
Yeah, I mean,
that,
-5 to 5. Yeah.
right, but is it possible that we could do reinforcement learning with policies that are statements or equations that are modified or
So
selections?
So for these finite MDPs, the action space is a finite space of actions. Those actions could be anything. It could be something very complicated. It could mean, like doing a pose or, a robot, doing a specific maneuver. But since the actions are discrete, we can enumerate them. So in this case, our actions are, -5, -4, whatever. I would enumerate them 1 to 11. Now, those actions 1 to 11 could easily be like each one of them could be an entire algorithm that you do. Like the action could be, like perform this entire sequence of steps, as long as that is a discrete action, which stays the same throughout the course of the problem. But,
Well,
this probability function, this is like whatever this action is, like, because this is a discrete problem, like we can always enumerate the actions regardless of how complicated they are.
right. But in a continuum.
Oh, continuous actions are different.
Hey, let me try to give you an example. Let's say I have 1,000 parameters, right? And I'm measuring some kind of system performance KPIs, right? And I want to decide what parameters to change to optimize a
Yeah,
performance, right? So
sure.
once I've gone through all my enumerations, well, none of that works, so I've got to try something different, right? So
in that
what
case,
other
you want your actions to be a change to some continuous parameters, right?
right,
Changing them.
right.
Yeah. So you could choose an amount of change that's reasonable, like 0.1 or 0.5 or 1, and say either go plus or minus that. That would make it discrete. So basically you can discretize the action space in that way.
Right.
And also if you go to like chapter 13, you can do policy gradient methods where you can actually use continuous actions. You would basically use a parameterized probability function to select the actions. And then the thing the policy is learning are the parameters of that distribution. So it would be like the mean output of a continuous value is what you would learn in the policy. But if you want to know more about that, that's if you can look at chapter 13, and there should be a video of chapter 13. But yeah, there is a way to deal with continuous action spaces. It's unclear how useful it is to actually have continuous actions. Sometimes it's more useful to just discretize the action space. It depends on.
I get that.
Yeah, it depends how important it is to you.
Yeah.
The other problem with having continuous actions is usually in general that can be negative infinity to infinity. And if practically your actions are really confined to a set of numbers, it's much more difficult to have the continuous action selection, be confined in that way. Now, actually, if you look at my notes for chapter, it's not covered in the book, but you can use like a squash distribution that forces the numbers in a certain range. And that's one way of dealing with it. but then you sometimes get stability issues with convergence. So yeah, there's different ways of approaching it, but the easiest way is
Right,
probably just to
okay.
discretize the actions.
Okay, yeah, you answered the question, Jason. Thank you very much. And did we do chapter? We didn't cover 13 yet, did we?
I did. Well, yeah, we did in the past. So
Oh, all right. I'll
yeah,
go
there was a
back and
past
look at it.
meeting. That's another part of the survey of whether, it would be people actually want to do those chapters again or just look at the videos and ask questions from them. But yeah, if you do look at, if
Did you put the
anyone,
link?
yeah, well, it's
Did
in
you
the
put the link?
meeting.
Oh, okay.
I can put in the meeting. Yeah, so in the meeting description on Meetup, like where the meeting link is,
Oh,
there's a
okay.
link to the YouTube playlist of all the meetings.
Oh, okay.
Yeah.
All right.
But
Thank
if
you.
anyone has watched those videos and has a question about a particular exercise or thing, you can, post it in somewhere, either on Meetup or in Discord. If I guess no one's put a Discord invite link in the chat, but maybe before the meeting's over, hopefully we'll have a Discord invite link. Anyone that wants to be in the Discord can join, and then
That's great.
ask questions there. Yeah.
Thank you,
Okay.
Jason.
That's good. Yeah. So any other questions about this car rental example or the solution? Okay, so let's see. We can, oh yeah, so there is this. Okay, so this is just to show you what you can do with policy iteration. So this last exercise here is asking you to modify the problem. So here the modification is there is an employee that rides a bus home and she can shuttle one car to the second location for free. And the other, so this is like, you now get one free transfer of a car from A to B if you want, if that's what you want to do. Otherwise she'll just ride for free. And also we can only keep 10 cars. If we have more than 10 cars, we have to pay $4 to store any additional cars, right? So the point of this exercise is, while these are like really weird arbitrary constraints, if you were trying to solve this problem with some kind of analytic method, once you start adding these weird constraints to the problem, you can no longer solve the problem with those types of techniques. But these types of constraints make no difference to the policy iteration algorithm. All we have to do is compute the new probabilities. So here is, yeah, the car rental. Okay, so actually my function I wrote to do the to make the MDP, I just added these arguments where I can have the employee shuttle or have a max overnight rate. It doesn't make it that much harder to compute the probabilities once you have this other way of doing it. And this is how the solution changes. So it looks a little more complicated. We can see now that there's a lot more instances where we transfer one car from A to B, which makes sense because this is a free transfer. So that part of it makes sense. The values are lower also in general, not at the bottom end. Actually, 430 is that. Yeah, so the bottom end values are a little higher. The top end values are lower. And that's mostly because if we're in this situation where we have 20 cars at each location, remember that we now have to incur this extra cost of $4 to store them overnight. So it does change. It changes the values, how much money we expect to earn in the long run, but it also changes the policy substantially. If we compare, this policy to this one. At the extreme corners, it's still the same policy, but quite a bit different in the middle. It's not that straightforward to understand, but it should be pretty easy to understand why this action of one is so frequent in this modified thing, considering we have the one free move from A to B. Yeah, but if you look at this, this function that creates this, that's where I have the overnight penalty and the maximum we can store each overnight, and then the employee, the free, but it's all accounted for, in here somewhere. when the probabilities are calculated. So yeah, any question about this exercise? 4.7. Okay, so the next technique in the chapter is value iteration. And there's sort of two ways of thinking of value iteration. I can compare it actually to policy iteration, or actually this policy evaluation. So, I mean, one way of thinking about it, but the easiest way to think about value iteration is we had done, the policy improvement theorem and policy evaluation, and we alternate between them. But we also had the Bellman optimality equation from the beginning, which says that the optimal value function has to satisfy this relationship. And if you look at value iteration, this update step where we start from one value function and then calculate the new value function, all this is doing is applying the Bellman optimality equation to all of the states in the value function. And in the same way that policy evaluation worked successfully, where we applied the Bellman equation, right? This was applying, so to do policy evaluation, we applied the Bellman equation as an operator to the value function, given a fixed policy. Here, we're doing the same thing, except instead of a fixed policy, our fixed policy is always just the maximization, or the greedy policy with respect to the old value function, which is the same as this Bellman optimality equation. And this, if we apply this over and over, this is just another fixed point iteration. And it turns out this also meets the criteria of what is required for fixed point iteration to converge. So this is like, we mentioned it briefly last time, but there are these requirements on the function where this has to be like a contraction operator on over the domain, and that happens to be the case. The other way of thinking about this, though, is actually if we compare this, we're just repeatedly doing policy evaluation here, except instead of working with a fixed policy, we're just always updating the policy every step, and we're updating it with the policy improvement theorem, where we're just taking the argmax, like the greedy policy. So the main difference here is you can either think of it as a fixed point iteration with this, or you can think of it as doing policy iteration, but where we don't wait for the policy evaluation to converge. Like, even though when we do this next update, these values are not necessarily converged to anything, but we still continue to modify. Like, we're never dealing with a fixed policy here, because this max A is always going to depend on these values, and we're always changing these values. So we're just continually updating, and we're like interleaving the improvement, and we're not waiting for it to converge. So there's two sort of different ways of thinking about it. I think this way is easier to think about it as just a fixed point iteration of the Bellman optimality equation. But, it's a more elegant algorithm, and that if you compare it, we don't have these two distinct phases that we switch between. We just do this same update repeatedly. And also, this allows us to very conveniently check if the value function is changing at all. Right here, you can see here, we look at the maximum difference between the new and the old value function as we go through the state space. And then we just stop the algorithm when this difference becomes smaller than some threshold. The threshold, this is just so because we're dealing with numerical, precision here. So we can't really expect this to be 0 per se, but we can expect it to get, arbitrarily small with, whatever floating point value we're using to represent the value function. So, this value iteration algorithm looks pretty compact here. You just need a way of computing this, basically, and taking the maximum of it. But this involves looking through again all the transitions from this single state and then maximizing over the potential actions. But that's what's being done here, right, with this Bellman optimal value function. This also should be noted, all these techniques actually require knowing this function, and we do need it again here in order to compute right, this quantity. So yeah, but then the value iteration becomes pretty simple. We just compute Bellman optimal value, and this is written again in a recursive style where we just keep calling this repeatedly until the delta is small enough. Actually, value iteration? Oh yeah, sorry, it's up here where we either have an n max or So here I also have it so there's some maximum number of iterations you can define, so it doesn't just run forever. But in general, like the halt criteria you want is for the difference in the values to be less than some threshold. So we can then, we can apply value iteration to the grid world example again. Here, right, each iteration here represents one sweep through the state space, right? That's what I'm showing here. So these are not converged values. If you compare it to the grid world example here, each of these iterations, the value function here has completely converged, right? So we actually have like the final converged values. And it turned out that we already had the optimal policy after one iteration. But each of these iterations is many sweeps through the state space, right? Because we have to do this entire sweep repeatedly until the values have converged. Whereas, for value iteration, each of these iterations itself is a much smaller task. And the grid world example here converges after just 4 iterations. So here we have the optimal values. And actually here, because I'm rounding, like I'm rounding to the nearest integer. You can see already, like it's already probably mostly converged after the 3rd iteration. There's just some minor decimal points that are changing. Is there any code on GitHub? Oh yeah, so actually, there should also be, for anyone that didn't realize this, in the meeting description, there's a GitHub link to the repository that has like these notes and like all of the code is implemented for at least through chapter 13 at that repository. So you see at least the implementations I did for it, if you were asking about chapter 13.
I just saw that. Thank you so much. That's great.
So I'm not the style is a little, like for chapters 1 through 13 or 9 through 13, all the code there's also like a package you can import and use all the algorithms. I mean, other people have implementations as well, but at least looking around, I haven't really seen any other repository that has like all of the chapter implementations laid out. But for these for these chapters in part 1 of the book, there is code in these notebooks, but actually most of it is rewritten. It's also in the repository. I ended up rewriting it in this notebook here, which is just an overview of part 1 of the book. And again, like I rewrote a lot of it because of the sparse matrix implementation. How like if you define that full probability transition function, it's usually very sparse, so you don't actually need to store all of it, and there's ways around that. So the implementations here just make it a lot more efficient. But so what's being shown here is still, it matches this pseudocode, but the result should be the same, but the implementation is a little different. So this is showing a value iteration on the grid world. You can also this is showing value iteration on the Jack's car rental problem. And you can see here that it took 88 iterations of value iteration to solve this, but it's still faster than the policy iteration, because remember, each iteration here is only like one sweep through the state space. And the solution should be the same. Yeah, it looks like it's the same solution. Yeah. So this is just to show the value iteration algorithm works correctly. We're getting the same solutions as we got for policy iteration, but the actual the book has an entirely different example to highlight the strengths of value iteration. So I guess we'll look at that now in case, but I'll pause a quick second to see if anyone has any questions about value iteration, the concept, the algorithm, or the, couple of examples we already saw solved with it. Okay, so let's look at the gambler's problem. This problem conceptually should be easier than the car rental problem. So yeah, so for this problem, we have capital, or just, let's say money, dollars, from 1 to 99. We win the game if we get to $100, and we lose if we run out of money. So we flip a coin, and we either get the money from the coin flip that we bet. So if we bet 10, we either win 10 or lose 10 on the outcome of the flip. Now, with a fair coin, this game is just trivial, right? It doesn't matter what you do. You have an equal probability of going up or down. So the question is, for this, when we're trying to find the optimal policy, given a bias of the coin, so here, PH is the probability the coin lands on heads, which is the probability that we win the coin flip. The question is, how much capital should we bet on every flip to maximize our chance of winning? Right. So here we're just looking at, like, this is an undiscounted problem. Right. If we win, we're able to walk away with the money. So the question here is just whether we just want to maximize our chance of winning or losing, not the, how quickly that happens. We can only bet the money we have, right? So if we have 50, we can only bet up to 50. And then if we were to bet 50 and win, we would then win because we'd have 100. And if we lose, we would lose on one turn because we'd have 0. So does that setup make sense to everyone? Just how the game works? Any questions about it? So this is showing the value iteration sweep. So each one of these sweeps is one sweep through the state space doing value iteration. So this is the value function. And it's important to note, unlike with policy iteration, right? Until it converges, none of these value functions are actually the correct value function for any policy, right? They're just an intermediate result. It's only when we get the final value function that we have both the optimal, the optimal policy and value function. So this curve at the top shows the value function for probability of heads of 0.4. So, right, this is a coin biased against us. Now, the closer we are to the winning capital, the higher the value, which is not too surprising. And then it just decreases as we get further away. Now, the policy here, now that they're showing a graph here of the optimal policy, or one of the optimal policies, right? We know that optimal policies are not necessarily unique. The value function is unique. So apparently, if you have capital of 50 and the coin is biased against us, the optimal policy is just to bet everything on one flip. And then similarly, if we're at 75 or 25, the optimal bet, right, is to bet 25, meaning we have a chance of winning in one go. Now, of course, it should be obvious here. Well, why not bet 75 here? Well, because there's no point in betting 75. That doesn't increase our chance of winning. All it does is increase our chance of ending up at a worse value. But then again, at 25, the optimal bet apparently is to bet 25 to try to jump up to 50 in one turn or lose. So apparently, even though this bet allows the possibility of losing in one turn, right? If we only bet one, we would not lose completely. We would get to live to play another turn. And then we have these other values here. But this policy function looks a little unusual. So the first exercise question, and for this is, you should probably think about this before actually attempting to solve this problem at all, is why does the optimal policy have such a curious form? In particular, for capital of 50, it bets all on one flip, but for 51, it does not. Why is this a good policy? So would anyone like to take a stab at this answer or have any thoughts about this?
Eric, why is it the gambler's ruin?
Gambler. Oh, yeah, I don't think this problem is exactly, I mean, this problem is a case, obviously, if the probability of heads is 0.4, this is a game which is, we're expected to lose, right? However, it's important to note that even though we're sort of expected to lose, there are capital states where we actually do expect to win, which is might be kind of counterintuitive. I mean, right, even though every flip, we're actually expected to lose the flip. Like if we start at a capital of 75, it's clear that we actually have a probability of winning which exceeds 50%, right? Because this value function here represents the probability of winning. And of course, right, I mean, this is assuming we're following the optimal policy, which is this. But this exercise question is really about, why does the policy look like this? And maybe, would you expect the policy to look like this? Like if I tell you, we have this game, you win the capital, you bet, the coin is biased against you. Do you have any intuition of, what the right thing to do would be? I mean, probably not play at all would be most people's intuition for a game where the coin's biased against you.
I don't know, not play too long.
Okay, well, not play too long is actually, I mean, if that is your intuition, I mean, that is the reason why you would bet 50 at 50, right? Because that's like,
right.
Let's just get this over with. Like, if I get lucky on that one flip, I'll win.
Right.
Isn't one of the reasons why the artifact of having a high policy for 25, 50, and 75 is due to not having a benefit of exceeding 100, since that reward state for victory is 100 or more.
Yeah. I mean, that's why, you would never bet more than 25, right? If you have 75, because you get no benefit. But I guess the other part of this is that, you're trying to end the game as quickly as possible. Although not here, right? I mean, here we could bet a value of a larger value for a chance to win on one flip. And here the selected bet is actually less than that. It's actually the bet that gets you to 75. However, it turns out that's not entirely true. We'll get into that in a second.
Does it have something to do with it being a little more discrete?
I mean, this is a discrete problem. Oh, you mean about which part of it? Like the part about why you would want to end the game quickly?
Like why it jumps from 5 to 10 to 50.
Oh, you mean like here? Yeah, yeah. I mean, it being discrete is definitely part of it because we have an exact dollar amount that makes us win exactly. Yeah. Um, yeah. I mean, I think what's more surprising about this probably is that you actually have a better than. I mean, your chance of winning, like here, if you look here, if we have a capital of 50, the probability of winning is actually 0.4, which is the same as the coin probability. What's interesting is that if we have more money, which you'd think like the game could go on longer from here, like, you know, if we're losing the game, in fact, from here, if we start losing, it'll last longer than here. And the longer it lasts, it's kind of bad because the more flips we make, the more we're expected to lose in the long run. But actually, the closer we are to winning, we do increase the probability of winning. Like if our capital goes higher here, which is again because of this discrete nature of the game. Again, like it's not something you necessarily expect to happen, but having the capital change does actually impact that. Well, anyway, so if you implement this, which is the next exercise, is to implement this with value iteration and actually solve it for different coin flip probabilities. So here it's showing the answer for 0.4. So here I'm going to show the answer again for 0.4. So we already saw this, right? This is the value function. These are the sweeps. Oh, and actually here, I'll make this 0.4. So actually, this is the optimal policy for 0.4. Here, they're showing a deterministic policy, right? There's only one action per capital value. Here, I'm actually showing the solution with all of the equally good actions. And it turns out for some states, there's more than one optimal action. You can see by the color. So if it's like bright white, that means that that's the only optimal action. And then if it's a grayer, you know, like the darker the gray, the more it's being shared between actions. Yeah. So actually, you can see here this 75. One of the optimal policies, which actually looks a lot less unusual, which is probably why they didn't include it in the graph in the book, is just the one that follows the top of this pyramid. So actually, it is equally optimal to just always bet. So that would mean if you're under 50, you always bet all the money you have. And then if you are over 50, you just always bet the amount you need to win if you were to win the coin flip. And that actually makes it a little easier to understand what's happening with the policy. So we're basically trying to win as quickly as possible or end up in a state which has an equally good expectation of winning. Since we know that all these higher values here, like the higher capital value we get, the higher the value is of the value estimate, then, you know, anything that brings us higher is better. And once we're past 50, we don't even have to settle for that. We can actually just go for the win immediately. So this does confirm the idea that winning quickly is better. What's a little harder to understand is why these other actions seem to be optimal as well. But the reason, you can get some idea of why that's true by looking at some of the other plots here. I'm trying to think if I have a plot. Okay. So I have this other plot here to visualize what's happening a little better. So let's look at 0.4. Okay, so let's see, capital. So let's say we have capital of 20, and the coin has a 0.4 bias. So from this diagram, you can see there should be two equally good actions here. One of which just brings us higher, and the other which brings us more to a lower state. So there's sort of like two different bets that we may make. Now, what's being shown here is the action value function. I'll zoom in a little bit. So right here, I'm showing the value function of the optimal policy. This is the action value function, meaning this is the expected value of each action. And then these are the two actions that share the argmax, right? So when we're finding the optimal policy, we're looking at this action value function. So this is like what happens depending on what action we take. And we pick the actions that are, the best. Here you can see by the shape of this curve how there are two of them that are equally good. And one of them is 20 and one is 5, right? So we have 20. So one is betting all the capital we have, all $20. And this is only betting 5, which would either bring us to 25 or to 15 in value. And this is showing the value function, the optimal value function. And for each wager, right, if we make a wager of 5, what this is showing is the state we end up in the value function. So we either end up like 5 more or 5 less. And similarly with a wager of 20, we either end up with 20 more or 20 less. And in this case, we lose. So each of these values, and of course, going up, right, we only go up with a probability of 0.4. We go down with a probability of 0.6. So both of these actions are ones where the balance between the risk of dropping is balanced out best by the benefit of going up in a different way. If we bet 20, we clearly end up with a much higher value if we go up. But then if we go down, we end up with a value of 0. And basically the shape of this curve and how separated these dots are is what determines the shape of this value function. And that's why you end up with 2 different optimal wagers here. Of course, that doesn't explain why the curve is shaped this way. And you see there are this curve, it's hard to tell on this diagram, but if you look closely at this curve, there are all these little, peaks in it, which affect the shape. I mean, even though it is a convex curve the whole time, there are these little weird, notches in it. Like this first notch happens at 50, and then there's a notch at 75. And that's again, due to like the discrete nature of the problem. If I change the capital value, let's say to like 32, let's try. Then we get a curve like this, right? And now we see there's 3 actions that are equally optimal. And again, on this curve, I'm putting the values here. But you can see like one of them, right, is a wager of 18. And that actually brings us to a value of 50. And then on the downside, we have 14. But right, we always have this one action which takes us up as high as possible, but then on the downside, we lose. But it's actually equally good to these other actions. But the other actions are ones that take us, oftentimes the goal is to get to these round numbers like 50 or 75. So, it's a little, but you can see what's happening inside the algorithm when it's picking the optimal action is it's looking at this action value curve and then picking the peaks of the curve. But, this exercise, the whole point of writing this out is to actually see what the problem looks like when we change the bias of the coin. So one question, so we know the coin starts at 0.4. So now another thing is let's solve it at 0.25. And I guess a question for people might be, if I change this to 0.25, so I'm making the coin even more biased against us. What do you think it'll do, to the solution? Either the value function or the policy function.
Well, I would expect that that curve to the value estimation of the curve to be basically more steep, and that would closer the closer to an extremely biased coin, or where the probability of winning would be zero, it would just get closer to a delta function where it's basically, don't even try to play that game.
And then what about the policy? So we expect the values to be lower, not too surprising. If the coin is worse for us, the value should be lower probably. But what about the policy function?
I would expect that behavior of having equally good policies to exist, but I would just expect that to be shifted somehow, though I'm not sure how exactly. That pyramid structure.
Would it flatten the pyramid?
I mean, I'll show you the answer in a second, but I'm just based on what you know about the problem. Yeah, it's just whether you have any intuition about how the policy would change. If you don't have any, intuition or, anything you want to think through, we can just go to what it actually looks like.
I cheated, and I wanted to ask a question. If I didn't notice if this was in the book in terms of the style of decision, whether it was risky, aggressive, or conservative, those 3 points earlier. I don't know if that's mentioned in the book as a classification of the decision making, but what I'm getting here is saying that the decision would be more conservative to avoid ruin. You mean, okay. I mean, are you talking about a more generic problem or this specific, MD? I'm looking ahead. You're talking about, okay, yeah, more conservative. Well, again, it's worth noting that even for this, this is pretty bad, right? Like 0.4, you wouldn't want to play a game with a coin this biased against you. But even here, right, there is a family of policies here, right? Like even if we have capital of 60, betting 10 and 40 is still considered equally good. So, one would be considered, I guess, more risky. The point is it's actually not more risky or more conservative. They're just both optimal in that case. And of course here, right, the coin's bias against us, all of these bets, and it matches here, right? From 1 to 10, there's only one optimal bet to make. All of them result in you losing after one flip, if you lose. Well, okay, I think if anyone else want to say something, or I'm just going to change this.
Well, what I was trying to say is that the ordinate would decrease. That's what I meant by flatten the curve.
Yeah,
That's
like you think
what
that the top, you wouldn't bet 50 at 50.
Right.
So you're saying you wouldn't want to end the game as quickly as possible if the coin became even worse?
No, just the opposite.
But if you flatten the curve, right, if you bet less than 50, you're extending the game because you have no chance of winning at 50 if you bet less than 50.
All right, well, then I'm misreading the curve. Then you would make it higher.
Well,
right?
No, this curve goes up to 50, right? So, yeah.
Well, the curve goes up to 50, right? But
this white square at the top means at 50, you bet 50.
Yeah.
And also here, it matches this. Right?
But what I was trying to say, at 50, you bet 0. That's what I'm trying to express. That's maybe.
Yeah, sure. Yeah, you can bet 0. So the problem with betting 0 is the game never ends, so you have an undefined value
function. Okay.
Yeah, unfortunately, betting 0 is allowed. We can bet 0, but the algorithm would never decide to bet 0 because betting 0 doesn't lead to any calculatable outcome.
Well, what I meant was that you would stop betting.
Yeah. But of course, I know.
You would do very few bets.
Yeah. That's not how the game works, though. The game either ends in a win or a loss. There's no option to walk away early.
Okay, all right.
Yeah, okay, here. I'm going to change this to point.
Could you show the graph which had the twin peaks, the two peaks?
Oh yeah, uh-huh. Well, this has 3 of them, but yeah.
So it looks like there's like a cycle, like it is a
Mhm.
optimal point where you
Yeah. This is for 0.4 also. So same
So
methodology.
can you play like for several days, like bet like $1 one day and then 5 the next, and then
Oh, you can bet a different amount every step. Yeah. This is saying if you have a capital of 32, right, this is what you should bet. And there's actually 3 equally good things to bet. But yeah, like the way this works is each flip is just a new opportunity to make a decision.
so how do you use like a time series to go about by making bets every day of the year, and then kind of find optimum bet based on my
Wait, but are you talking about if you change, because if the bias of the coin is 0.4, right, we already have the optimal policy here. So the question was about changing the bias, but are you talking about an alternative way of solving the problem?
Yeah, I'm questioning the bias because I'm not very sure the bias. Like I could.
Oh no, this is given to us. This is part of the problem definition.
Oh, okay.
Yeah, it's like we're told ahead of time, right? We have a bias. Now you could actually also solve this problem where we have an unknown bias, which itself is randomly distributed. But then you'd have to, I guess, ask the question of whether the coin was potentially changing every flip, or if there was a family of coins that you picked from ahead of time. But yeah, that would make it more complicated. And probably ruin also the Markov property of it, maybe. But yeah, no, this is like the bias is part of the definition of the problem here.
Gotcha. Thanks.
Okay, so here, I'm going to change it here. I'm going to change it to here 0.25. Okay, so here's the new value function. So what Dimitri said, yes, it is a steeper curve, right? I guess we can quickly go back and forth between them and see. So actually, we didn't do 0.5, but 0.5, interestingly, the curve is flat, right? Because we don't expect, the values are actually linear from one. But so this is 0.25. So the curve gets more severely, concave, meaning it gets closer to 0 faster from here. We still do have this, we still have this probability of winning greater than 0.5 for a capital of, like if we have a capital of 90, for example, we have like about a 60% chance to win, even with a coin which is this bad. But so it looks like the policy is the same. I can actually, let's try this with 0.1. So now value curve, even more concave and also more weirdly shaped, right? It exaggerates these notches in the value function. But yeah, apparently policy is still unchanged. And then if we do like 0.49 also, so 0.49, we're close to 0.5. These curves in the value function are now very minimal, but we can see the same policy. So apparently any coin which has a bias against us, it doesn't actually change the policy. The policy is still the same. We try to end the game as quickly as possible. So did anyone think that ahead of time? It didn't seem like anyone claimed that was true. But now that you've seen it,
I
does it
guess
make
I was
sense?
trying to say end the game faster or sooner, which I think somebody.
Well, we're already doing.
said,
Sure.
Yeah,
we already are. Other than, of course, these bets don't do that. But what they do is they take you to states that are in all the policies seem to try to attempt to get to states like here or any of these. But once we're in this part of the curve, we can either go for the win immediately, or we can go for an action that takes us either to 50 or 75, right? What all these actions are doing is let's say we have a capital of, like 60 or something. We can either try to win immediately, or we can risk ending up like, or try to get to 75 immediately. Apparently trying to get to 75 isn't a problem. Like, it doesn't ruin what we're trying to do, right? Where that's like this bet of 10 here.
Right.
Is that, or a bet of, yeah, something. So yeah, we're basically, yeah, there's like certain specific states we're trying to get to. But if you were trying to remember a policy, the easiest one to remember is just the top of this curve, right? Where we just bet either as much as we can or as much as we need to win. Okay. But then the next modification is to say, well, what if we make the coin have bias in our favor? Then what do you think will happen to the policy and the value function?
Well, the value curve should become more horizontal, right? Or more not horizontal, like a 45-degree.
So I did already show
Oh.
0.5.
Right.
This is actually a completely straight line. At 0.5. But at 0.5, this problem is actually trivial. In terms of computing the values, whatever we do, we expect equally to move up or down, and it makes the whole thing symmetrical, which makes all the value calculations really trivial. But now we're asking about if it's actually in our favor by 5%. Oh yeah, sorry. We can also look at this curve here for the case of 0.5. We can see it, indeed, everything is flat, right? Like there's no.
Yeah, it's horizontal. That's exactly right.
Yeah, well, this is not the value function. These are the action values at this capital. And this is saying that whatever action we take, we end up with a 50% chance to win. So if the coin is 0.5, we actually have a 50%. Well, this is at a capital of 50. If I change this to like 80, let's say. Now,
that's interesting.
Yeah, so 20. So if we have a capital of 80, according to this, we actually, if we bet higher, well, obviously, okay. These numbers are a little weird, right? Because obviously, if we're at 80, we never need to bet more than 20 to win. So it just means that all of these bets, we still expect an 80% chance to win. Yeah, because it's all symmetrical, right? So if we have a capital of 80 and the coin is fair, we have an 80% chance of winning the entire game. But then that's mirrored by all of these wagers have these pairs of outcomes that actually keep the expected value equal, right? Because so we go up 5 and down 5, and the probabilities are all linear. Everything's linear. So everything just ends up keeping the probability of winning the same, right? Because we have an equal chance of going up or down. Once we get up here, though, we do have a higher chance of winning, right? But the point is we had an equal chance of ending up down here. And, we have an equal chance regardless of anything. So that's for 0.5. 0.5 is trivial. But what about for, 0.55?
Well, for the policy, I would expect behavior in order to keep the game running as long as possible, because every single action actually increases the probability of actually winning, I think.
Well, yeah, because we have a higher chance of moving up the value curve in that case. Of course, I haven't showed you what the shape of the value curve is, but it's probably safe to assume that the values are higher, the higher the capital. We don't know exactly what the curve is shaped like. So because we have a 55% chance of moving up the value curve, we want to increase, I guess, the number of opportunities we have to move up the value curve, which would mean more turns. So yeah, the intuition probably would be, as Eric said, bet smaller, or probably more precisely, bet as small as possible, which would be 0, but betting 0 doesn't really mean anything. So 1 would be the smallest, reasonable bet to make. Okay, well, let's just see what it looks like. So this is the value curve here. And these are the bets. Now, it looks like there's some stuff going on the right side of this curve. I believe that all of this is actually numerical noise, because this curve becomes so flat that it makes it look like there's a family of actions that are equally good. I don't think this curve ever becomes flat. I think it's just a numerical precision that makes it flat, lack of precision. Of course, if the curve ever did become flat, all these bets that are spread out are just keeping you in the flat region of the curve, which is why they're all equally good. But I think if you did this with infinite precision, you would find that actually a bet size of 1 is what you would want for every capital stake. And we can see here let's see if we make this 0.55. Yeah, here we have the action value curve. And again, it looks flat, but I think actually it does get higher the closer we get to 1. These values I don't think are actually 1 here. I think they're slightly less than 1. Yeah, we only get a value. Yeah, so it should get higher like the closer we get to a bet size of 1. So yeah, we do have some numerical noise probably issue here. But even with these values, right, betting 1 is still optimal even for these choices. Are your results stable as data? Oh yeah, this is asking about the numerical stability of this. Yeah, I mean, I think as you make the precision lower, you wind up having more, you'll end up seeing more deviations from this at lower capital values, because you have trouble distinguishing the curve shape as it gets close to 1 up here. Luckily, if you do make a mistake and bet too much, the worst thing that'll happen is you'll end up in this part of the problem where you're going to bet 1 again, and you're still betting optimal. But yeah, the intuition is if the coin is in our favor, we want to extend the game as long as possible. And if it's against us, we want to end the game as quickly as possible.
Cool.
There's also, this problem is undiscounted. If you make the problem discounted, like if I set this to 0.9, let's say, now we're actually trying to win faster. And that changes the solution a lot. Now we actually, if we're greater than 50, we are actually back to betting. And of course, this solution will actually depend on the discount rate. If I make this 0.99, it'll change the region of space over which we try to win in 1 turn. Right. So this, again, is another way of making the problem more complicated, which in real life, it might depend on like if there actually is some future time at which it's impractical to wait that long for a win. Then this actually tells you sort of the precise time when it's worth taking that extra risk of going for it. And then less than this, you're still back to betting smaller amounts. Some of these exact values might, again, be due to numerical noise, and it might be hard to distinguish exactly what's happening here without higher precision. But you can always look at the action values themselves to see better what's happening. And if there's not much of a difference between bets, right? Because here we're showing the argmax here. So the argmax is like a really noisy function. Like if something is just slightly better, it'll jump out. Whereas we really care more about actions that are, within some numerical precision of being optimal. And it may end up spreading out these points a little more. Yeah, okay. So are there any other questions about this gambler's problem or?
So you think it's finite register length effects that are causing that anomaly?
Which anomaly?
This
at the end,
or
the
this?
build up. Well, it was also on the other slide too, but yeah, and I think it's the same.
I mean, I think this region of the solution is probably correct. This region might, this is probably correct too. Here,
well, go back to the other picture where there was like a flat distribution to the very end. No, on the policy curve. On the policy curve. There was an earlier iteration where the policy had a different shape. It was flat until it got to the
oh,
far
you mean
right.
this?
Yeah.
Mhm. Yeah, I don't think, I think, right, this spread out of the actions is because of this, right? It's because we're getting closer. Like, if I have a capital stake of 1, or wait, maybe I'll try. And yeah, so if we have a capital stake of 10, the action value curve is more, there's a larger difference between the action values. So we can clearly see that this bet of 1 is better than this bet of 2. Once we get closer to winning, like if we get to like 99, this whole curve, or wait, 90, I'm not sure why.
The delta is smaller, right?
Yeah, so I think we're getting more into like, because it's not showing. Yeah, this curve now is getting really
precision.
Yeah.
Register length.
Yeah.
Okay.
You could probably prove somehow that this curve is strictly increasing out to here, even though it appears to like be flattening out. Yeah. See here, these jumps here in value. Yeah, that being said, it may not be, some of these jumps that you see in the solution are actually because of the discrete nature of the problem, not because of the numerical precision.
Yeah.
So it may actually be that this action, but no, I mean, it can't be a probability of 1. Yeah, no, I think it probably is numerical precision, right? Because like, there's no way that, like, we know that you don't have a probability. I don't know, actually. I'm a little undecided about this. I find it hard to believe that any of these have a value of 1. The question of whether they're actually equal is different. Actually, wait, these values are maybe it's not 1.
Well, I mean, if you were to change your variable to make it like a 64, 128, 256 bit resolution, you're saying that problem will go away, right? Or,
Go away. Okay, I mean, I'll show you one example here. This is solving it with 64-bit precision. I'll change this to 32.
So it should be bigger then.
Yeah.
Yeah, it is.
Now we see.
Okay.
Yeah.
That's it.
So
that's it. Okay.
Yeah, I mean, 64. I don't, again, like this doesn't prove that if you went up to infinite precision, this goes away. I think it probably does. But again, you have to be a little careful because even though it seems intuitive, we'd always bet 1. This is a discrete problem. Yeah, but I would guess that the optimal bet should be 1 every time.
All right.
Yeah. But again, like you can't use a lot of traditional techniques to solve this, right? Because you have like, right, if you have a capital of 75, the coin's bias against you. There's all these trajectories where you end up winning before you lose, even though you should, intuitively, you'd expect to lose regardless. But because your barrier to winning is closer to where you are, you actually have this 60% chance of winning here. So some of your intuition fails when you have these discrete problems. It gets a little weird. And it would be very difficult to solve this without these sorts of techniques, which is actually, maybe I should get to, there's this comment here. Wait, is it? Yeah, actually here about the efficiency of dynamic programming. And these techniques, even though they appear to be, could be somewhat inefficient, we have, if n is the number of states and k is the number of actions, these methods generally you can show in the worst case scenario converge in some polynomial time as a function of the number of states and the number of actions.
Now, if you compare that to trying to look through the space of policies that we'd have to consider, there's like k to the n policies, assuming like we could choose a different action at every state. And then if you also look at the space of trajectories, which is like actions and then states you end up in all the way to the end, that's an even larger number of things to look at. So these dynamic programming solutions do an exhaustive sweep through the state space, which sounds like a lot, but it could be a lot worse. A sweep through the policy space or a sweep through the trajectory space would be completely impractical, even for a simple problem like this. And that's one of the reasons why these techniques are so much better than other ways you could solve these problems. So it's actually quite efficient when you consider that it's only polynomial time in terms of the number of states and actions, right? If you were trying to like think about, we have a bet of 50, think of all the different trajectories of going up and down this curve you have to account for. Whereas here we define it and there's this sort of recursive solution where we have a dependency between the state values, and that allows us to completely ignore all of those, n step trajectories that could occur here. So that's one note, about why these techniques work. The other concluding parts of this chapter talk about, how when we do, like here, let's just take value iteration as an example. Here, we go through the state space and we keep looping and updating. You don't have to do it this way. We do have to, in general, visit all the states continually, but we don't have to visit them equally often. So one option could be, we could imagine like having our value function, however it is at the moment. We can use that to make a policy that we think, is the optimal policy we think of at that moment. We could have an agent interacting with the environment using that policy in like one parallel task. And it could be adding to like a queue of states. So that way we could have this accumulated list of visited states, and we could see how frequently they're visited. We could then take that queue, feed it in to this value iteration algorithm where instead of looping through all the states in the state space, we loop through the states that we visited, and maybe we add in random states on top of that to make sure that we visit all the states. But it's a way of focusing the updates on the states that we actually visit. You do have to be careful to make sure, you don't neglect states completely, because when we do this max update, right, we use these S primes, and we have to have value estimates for the S primes as well. Like, so if there's some S prime that we think has like a bad value and we ignore it, we never visit it, we never update it, we could end up, that's where the algorithm might not converge properly. So, but doing this asynchronously where like you imagine having one process tell you what states to visit, the other process updating the state values, and then we sort of interleave them arbitrarily in time and we throw in. It's just a way of maybe making these state visits more efficient. Yeah. And then the other note at the end here is on this concept of generalized policy iteration, where when we did policy iteration, the first one, what we do is like this. We start with the value function, or whatever. We start with a policy, we fully converge a value function. Then we fully form the greedy policy, then we fully conform a new value function, right? And we do this back and forth. In generalized policy iteration, we don't have to follow these arrows to their completion each time. Like here, we could only, like when we do value iteration, we only update like the optimal policy for the state like we're visiting at that moment. And then the value update also only happens for that single state. And we sort of cut all of these arrows short. But the point is, however we interleave the two processes, they still end up converging to the optimal policy and value function. And however we do the process, if at any point we don't see a change, like when we do the policy improvement, right? Where do we have the thing on? policy. Yeah. Like, well, this is when we do policy improvement, right? We choose the new policy like this. If we ever do the policy improvement and it's not changing, or we do the value update like this and it's not changing, we know we have the optimal answer. So even if we're not sure if the thing we're doing is, going to converge or is, working properly, we still have a way of verifying when we have the correct solution. So it will. It turns out if we interleave these processes, it will actually converge as long as we, visit all the states, continue to visit all the states with some frequency. But even if you think you've like completely screwed up the process, when you do that evaluation of like, is this the optimal value function? You can always check if it's the optimal value function because it will have to satisfy that Bellman optimality equation. So that is the other major point. And then, yeah, that does conclude the chapter. So then if you look at the YouTube playlist, the next chapter is chapter 5 on Monte Carlo methods. These are methods where we don't have this function necessarily. We don't have access to these probabilities, but we can sample from it. So we have a way of like simulating transitions in the environment, but it's sort of a black box simulator.
I was going to say, is it possible you could make the analogy, even this is dirty all the way around, but you could have a bad gambler, right? And you could have dirty approximations similar to the famous stochastic gradient descent. You're sampling randomly.
Yeah, I mean, these Monte Carlo methods, yes, end up sampling from the transition function where we don't have access to it. And then using those samples, we estimate values. And it's the same idea, though. We still try to compute a value function and then do policy improvement with that value function. It's just that in this chapter, we're doing what are called expected updates, where we're actually computing all these expected values for real because we have the probability. Like this calculation inside of this max operator, this is an expected value. In these methods, all we're doing is instead of this, we're just replacing this with a sample, right? So we have an unbiased sample. And we have to sample a lot, right? Because we're not going to get a good estimate unless we take a lot of samples. So this is a lot less efficient, right? We would much rather just know the probabilities and do it that way. But it turns out, we can gather these as we go and do it that way. So there's already a video for this chapter and already like notes and all the, all the material for this is already online. So you can look at that. And I guess, so we'll have to decide what to do next time. And I guess what most people want is some sort of like case study example. So I'll think about that. If anyone wants to like join the Discord or you can also send a message on like GitHub or Meetup in any number of places, write a comment anywhere. If you have an idea of like a case study you would like to look at or think about, feel free to send a message. But yeah, I'll think about what to do. Again, the other option was like going over specific questions people had for other chapters, but that will probably take longer to figure out because people would actually have to post questions or things they're confused about. But yeah, there were some other examples in the book. I'm trying to think. There were already some case studies I had looked at or was working on. And depending on the case study, like one or more of these techniques might be appropriate for it. So yeah, we'll have to pick.